All right, let's look at section 3.5 in the book. It has to do with discrete time systems. Probably the biggest rule you've got to know is that is the condition that leads to stability or instability of a system. And I kind of drew a little thing here for, if you remember in the complex S-plane for continuous time system, we had to have all of the poles in the left half plane. The condition for discrete time systems is somewhat different. They still have to be located in a region, but now the region isn't a left half plane, it's the interior of the circle. Here's the rule. A causal, linear time invariant system is stable if and only if all the poles lie inside a unit circle on the z-plane. And in polar coordinates, that means that the radius of all the poles has to be less than 1. Okay, if that's not true, if even a single pole lies outside the circle or on the circle, that's an unstable system. Well, here's an example where I've written h of z, and I've gone and factored it, and we see, I've got complex. There's a complex 0. There's a complex 0 that's, and these always occur in complex conjugate pairs. So this 0 is the complex conjugate of that 0, right? Because this is a plus j, and that's a minus j. That means they're complex conjugate pairs. The denominator also has complex poles. Like, for example, from there to there is the first pole, and we see that it's the complex conjugate of the second pole, P2. So P1 and P2 are complex conjugates of each other, and the similar thing for the zeros. And we always expect that for the kind of linear systems that we're dealing with. In order to find the pole zero plot, see, I want to sketch the pole zero diagram and determine stability for this system. First thing that I recommend doing is to multiply the top and bottom by z cubed. And what I want to do is express this thing in positive powers of z. These inverse powers of z are sort of confusing. So if we rewrite this in terms of positive powers of z, it's a little easier to interpret what the poles are and what the zeros are. So multiply this by z cubed over z cubed, right there, and multiply it through, and you can see, I hope, that this is the result. We have z times z minus z1, z minus z2, and on the denominator, z minus p1 and z minus p2. Now, with this representation, it should be quite clear where the zeros are. There's a 0 whenever z is equal to 0, and so here's the z-plane. Z-plane. And I always start by drawing a circle. This is the unit circle. In other words, it has radius of 1. This is the real part, of course, and the imaginary part. Well, this 0 is at the origin. Whenever z is equal to 0, then h of z is equal to 0. So I've kind of drawn it there at the origin. This 0 is at 1.2 e to the j pi over 4. Where is that? Remember your complex numbers. 1.2 is the radius. Pi over 4, without the j, is the angle. So if I go 1.2 at an angle of pi over 4, remember that's 45 degrees, and I go out a distance of 1.2, remember this circle is a radius of 1, so it's beyond that, there is this 0. And I've shown it 1.2 e to the j pi over 4. There's another 0 that's the complex conjugate. That means same thing, only it's rotated to minus pi over 4. Okay, minus pi over 4, minus pi over 4. So those are complex conjugate pairs. The zeros are at 0.5 e to the j 2 pi over 3 and 0.5 e to the minus, there should be a minus there, j 2 pi over 3. Okay, let's show it there. So 2 pi over 3 is an angle that goes over into this quadrant. I won't draw it because my diagram's getting kind of messy, but it's from here over to there is 2 pi over 3, and the angle and the radius is 0.5, so it's half the way out to the unit circle. So we get these two poles corresponding to P1 and P2, which are shown here, P1 and P2. Well, is it stable? The answer is, are all the poles, there's only 2 of them, inside the unit circle? Yes, it's stable. All the poles are inside the unit circle. What about these zeros? Zeros are outside the unit circle. They don't affect stability. So zeros do not affect stability. So anyway, continuing on with the discussion of systems, discrete time system theory, a little bit of discussion on terminology. Here's a general form of an h of z, just numerator, denominator polynomials in z. If n is equal to 0, that's this n, we call this an all-zero system, because if n is equal to 0, then all of these terms are 0, so there's only a numerator. There's no poles, only a numerator, called an all-zero system. There's an example. Y is equal to 3x plus 2xn minus 1. It's completely feed-forward. There are no feedback terms. And as we discussed earlier, this is a finite impulse response or non-recursive system. And here I'm getting ahead of myself. An FIR h of n would look something like this, and then it would be 0 for all time. Okay. What about when n is bigger than 0? So there are some a coefficients, there are some poles, and let's say that m is bigger than 0. We call that a pole zero system for obvious reasons. It's got poles and zeros. Here's an example I've sort of jotted down ahead of time in red of a pole. Well, actually this is a all pole model that I'll get to in a minute, but this is a recursive system where we've got the output in terms of previous outputs. So it's an IIR system. There's a h of n for an IIR system. It goes on forever and never dies to 0. When n is 0 and m is 0, when n is bigger than 0, so there are denominator terms, but no numerator terms except for that constant, that's called an all-pole system. And this actually is an example of an all-pole system. Okay, so there's just some terminology. All-pole, pole zero, all zero, and of course you have to know whether they're FIR or IIR. And the last thing I want to mention is when we're counting up poles and zeros, we don't usually count the poles and zeros that occur at the origin. They don't affect things very much. So when we're talking about all pole or all zero, that doesn't include poles or zeros that may be at the origin.